Hello, and welcome to Amazon Web Services webcast, Getting Started with Amazon DynamoDB. Before we begin, I would like to walk the audience through a few items. On your screen, you can see a Q&A pod. Please submit your questions for our presenter at any time during this webcast. Our Q&A moderator will answer them throughout the presentation. We'll also address them in a live Q&A session in the end of the presentation. Today's webcast is being recorded, and we will send you a follow-up email with the URL to the recording once we verify the recording quality, as well as a link to the presentation deck. And again, welcome to today's webinar, Getting Started with Amazon DynamoDB. Our presenter, Nate Slater, is the Solutions Architect at AWS. Nate has been working in information technology and software engineering in the Bay Area for the better part of 2 decades. Prior to joining Amazon Web Services as a solutions architect, he spent the prior 12 years building software for the healthcare and life science industry. He has deep experience with object-oriented programming, service-oriented architecture, and both relational and NoSQL database systems. Now, Nate, you have the floor.
Thank you. Today, we are going to be talking about DynamoDB and how to get started with DynamoDB. Thank you all for coming. So let's get started. This is the agenda for today. First, we're going to talk about what DynamoDB actually is. For those in the room that are new to AWS or new to Dynamo, this will be a good introduction to what the DynamoDB service actually does. Then we're going to walk through some of the DynamoDB fundamentals. This is where we'll really get into how DynamoDB works and how you actually program against it and use it as a database in an application. Finally, we'll talk through some of the typical workloads that we've seen customers at AWS using DynamoDB for, and some of the use cases as well that we see. And then finally, at the end, we will do a demo. I will show you how to program some code against DynamoDB just to do some basic operations like create tables, insert items into tables, and retrieve items out of tables. Okay. So let's first start with the question, what is DynamoDB? So DynamoDB is a fully managed NoSQL document and key value data store. So pretty simple definition, but let's parse out some of the key components of this because there's a lot to understand here. First, let's look at NoSQL. So the question that maybe some of you are asking is, well, what is NoSQL? And there's a lot of definitions for NoSQL, and I think you can maybe get into trouble trying to categorize NoSQL in one specific way or another. But in general, I would say that NoSQL is a term that is used to describe data stores that trade the full ACID compliance that you typically find with a relational database management system for high availability and scale. So let's dig into that statement a little bit now. So ACID compliance, the ACID acronym, is basically a set of features that you typically find in a relational database management system. The A stands for atomicity. In a NoSQL database, you do have atomicity, meaning you can take operations and make them look like they're executing like a single operation. But generally, atomicity is only for a single row or a single item. This is not the case for all NoSQL databases, and that's important to understand, but it's a typical pattern that you'll see with NoSQL databases, that you can have atomicity on an operation, but really only if you're updating a single row or a single item in the table or database. The C stands for consistency, and consistency is basically how your data looks at the end of a series of operations. And typically with NoSQL databases, because they are distributed, and we'll talk a little bit about the architecture in a few slides from now, you'll oftentimes find that they have what's called eventual consistency. And what that means is that 2 clients reading data from the database at the same time may actually get a different view of the data. The I stands for isolation. Isolation is very closely related to consistency. When you talk about isolation in a relational database, you're basically describing what clients can see as a transaction is occurring. And in some NoSQL databases, you can actually have something called a dirty read. And what that means is that a client may actually get a read of data that never actually gets committed to the database. And again, for those coming from the relational database management world, that may sound pretty scary. But we'll talk a little bit about why, when you're dealing with NoSQL databases, this doesn't usually result in a problem. And then finally, you have durability. Durability is something that all NoSQL databases do provide, and they provide it very well. The difference is that the durability in a NoSQL system really comes from replicating data on commodity storage hardware. So rather than having very expensive SAN or NAS hardware with lots of redundancy built into it, NoSQL databases tend to take the approach that if you make enough copies of your data, say 3 copies of every item in a table, and distribute those 3 copies across the nodes in the cluster, you essentially will have very good durability. You could lose up to 2 nodes simultaneously, and you'd still have a copy of that data. So let's talk a little bit about why you would use NoSQL. As we just pointed out, NoSQL databases oftentimes will have isolation level that allows dirty reads. You have eventual consistency. You have single row transactions only. None of these really seem like they're all that great if you're used to the full ACID compliance of a relational database. But there are some reasons why NoSQL systems make a lot of sense. So when you're talking about traditional SQL databases and comparing those to NoSQL databases, when you want to scale a traditional SQL database, generally what you need to do is just basically make the database bigger. And so you can see from this diagram here, you start with a small database on a small piece of hardware, and if you want more scale, you're basically going to run that database on a much larger box. If you want high availability, you're going to basically have 2 of those boxes. One is going to be acting as a primary, and it's going to be handling all of the actual work until something happens, and then it will fail over to the secondary. And so you can see in this scenario, you may end up in a situation where you have 2 very expensive, very large, vertically scaled out boxes that are running your database, and one of them is essentially sitting idle while the master is handling most of the load. And this is what's called scale up or vertical scaling. So in the traditional database world, this is how you would achieve scale and availability. Now on the NoSQL side, things are a little bit different. In the NoSQL world, you basically scale out by just adding more copies of that small database that you already have. And sometimes you can do this by adding more nodes to your cluster. Sometimes you could do this by partitioning or sharding your data, where basically you're going to split your data across all the nodes in the cluster. There's a lot of different strategies that NoSQL take to do this. But they all sort of share the same general principle, is that you, instead of scaling up, you're going to scale out. So as you need more capacity in your system, you're going to just add more servers to your cluster, nodes to your cluster. And that also helps you with availability, because now you no longer have a single point of failure, right? You can actually distribute load to different nodes in the cluster. And again, various NoSQL databases take different approaches to do this. You have some that where any node in the cluster can handle any incoming request. And you have others where they do actually have the notion of a master node, and they have ways of replacing the master node if something happens to it. But the idea is that in effect, one or more of the nodes in the cluster, possibly all the nodes in the cluster, could handle an incoming request from a client. So there are some differences in strategy here in scale up versus scale out. If you scale up, generally you trade complexity for cost. So you can scale out to a bigger machine. You may not have as much complexity as you would in the scale out approach, where you have to deal with a cluster of machines. But generally, the bigger and more powerful the hardware, the more cost you incur. And so the other approach, the scale out approach, basically says, well, keep costs low and scale out. You will end up with some complexity in your cluster, but you can do it at lower cost. And I think there's one important element that's not captured on this graph, is really when you're scaling up, at some point you're going to hit a limit as to the biggest and most powerful instance or server that you can run, right? There is an upper bound there. Whereas if you scale out, in theory at least, you can scale infinitely. You can add as many nodes to your cluster as you want. And that's a big reason or compelling reason to use NoSQL. There are some trade-offs, and this is where we get into the reason why most NoSQL databases cannot enforce full ACID compliance, and it has largely to do with something called the CAP theorem. CAP theorem was proposed some years ago. It's a distributed computing concept that essentially says in a distributed system, a network partition is going to happen. And so you can see on that diagram on the left, we have a bunch of database nodes in a cluster, and that orange line is showing a partition has occurred. And so 3 of the nodes can no longer communicate with those other 2 nodes. And there are some consequences of this, and that's essentially what the CAP theorem tries to capture. The CAP theorem essentially says that you can be tolerant to that type of network partition, but if you are, you can either be consistent or available, but you can't be all 3. And so a CA database, a consistent and an available database, that's like a traditional relational database, right? It's not really tolerant to a network partition. A NoSQL database, on the other hand, may be called a CP database. That means it can provide consistency of data and it can be partition tolerant, but it can't be 100% available. Alternatively, you could have an AP NoSQL database, which will be 100% available, even in the event of a partition tolerant, but not fully consistent. And if you think through this a little bit, and this gets into some sort of detail around the consistency and isolation models found in relational databases and NoSQL databases. But if you think about it, if you're going to be consistent and partition tolerant, but not available, probably what that means is you have some sort of master node in your database. And if half the cluster can't talk to the master node, well, you can guarantee consistency because the master node will still be able to serialize those writes in a predictable way. But at some point, there will be nodes in the cluster that aren't available due to the partition. The alternative being available and partition tolerant means even if 2 nodes are separated from the other 3 nodes in the cluster, any one of those nodes can handle an incoming request. So you can be 100% available during the partition, the network partition, but you may have some consistency issues because if node 1 handles a write for the same item as node 3, and node 1 and node 3 can't talk to each other for some length of time, who wins, right? When the network partition heals, which write actually wins? And NoSQL databases have varying strategies for doing this, but it has some consequences into the consistency level of the database. So CAP theorem is very, very important when you're working with NoSQL databases. Okay, so let's revisit our question, why NoSQL? Horizontal scaling allows for infinite scalability, so we just talked through that. It's cheaper to scale out than to scale up, so cost is a big driver here, right? Oftentimes you want lower cost, and you can get that through the scale out approach. It's not something you can easily do with the scale up approach. And you can get full consistency or full availability during a network partition. So again, in a distributed system, that's generally desirable, right? You want to basically have a system that scales. You want it to be available most of the time, if not all of the time, and you want basically to avoid sort of some of the single point of failure risk that you would have in a single node system. And then, as we'll see when we walk through some examples with Dynamo, full ACID compliance is often not needed, right? When you're dealing with certain types of workloads, we see a lot of workloads where data never changes. It's written once. It's immutable data. You don't really need some of the same types of isolation and atomicity and consistency that you would have with a relational database there, because you're not actually changing the data. Durability is the one sort of piece of that where I think you get both in either a traditional system or a NoSQL system, but the atomicity, consistency, and isolation will vary. Okay, so now let's go back to our original question, what is DynamoDB? And let's hone in on this phrase here, fully managed. And this is, I think, very, very important for those that are new to DynamoDB because understanding what a fully managed service is, I think, is crucial for understanding how powerful DynamoDB can be when compared to other NoSQL databases. So what is a managed service? So basically, a managed service is a web service in which consumers of the service never need to interact directly with the underlying compute, storage, and network resources. So it's a little bit of a mouthful, but basically it means that as a consumer of the service, if you're going to write a client that talks to, say, DynamoDB, you never need to know anything about the underlying servers, the storage that's attached to those servers, or the networking between those servers. All of the interaction that you make with the DynamoDB database is done through an API. So why is this important? So why would you use a managed service? I mean, if you think about it, we've got EC2 and VPC, really great, very easy to set up networks in the EC2 system in a region of your choice. And you can see here, this is a pretty straightforward, configuration. I've got my VPC and I've got a single subnet that's in US West 2A. And, not so bad, right? I can create this through the console in probably about 5 minutes. It's probably about, 25, 30 lines of CloudFormation if I wanted to automate this. Well, so if we want to really have a distributed system that's available, probably what we're also going to need is a second availability zone, right? So, minimum, if we're going to build out a NoSQL database ourselves, let's say we were going to install, something like HBase or Cassandra. There's a lot of really good open source NoSQL databases. Let's say we decide we want to build it ourselves. At a minimum, we're going to need 2 availability zones. And that doesn't add a whole lot of complexity in terms of the EC2 networking piece. The availability zones, they will be on separate subnets, but you'll still be able to talk to instances very easily across availability zones. But there is a cost, right? You're going to pay a penny a gigabyte for every bit of data that's transferred across those AZs. Now we need to bring up our clusters, right? So we're going to bring up a cluster of instances in one availability zone and a cluster of instances in the second availability zone. And here's where things start to get a little more complex, right? We're going to need to evaluate what type of EC2 instance is going to work best for our database. We have to look across networking throughput. We got to look at I/O requirements, memory and CPU, right? All these things are important. And fortunately, EC2 has a really, really rich variety of instance families, but it's still going to take a little bit of work to figure out which families are going to work best. And we got to bring up some number of those instances in one availability zone and some number in the second availability zone. So looking at this configuration, you'd think, well, hey, we're looking pretty good, right? We're multi-AZ, that gives us good availability, good durability of our data. We're replicating across AZs. We're done, right? This is basically all you need to run a NoSQL database. Well, not quite. Typically, you're going to need some kind of shared configuration or coordination framework like Zookeeper. And the reason is that these nodes in the cluster are going to need to know about state of other nodes in the cluster. And so in order to decouple the state management from the cluster itself, you've got to put it someplace else so that if something happens to the primary database cluster, the nodes that are still alive can actually get to that data. And so you're going to run a separate cluster, and again, in NoSQL world, a lot of times that's something like Zookeeper. And so now you've got more instances to manage, and you've got replication across that cluster. And oh, by the way, Zookeeper itself could be considered a NoSQL database. So you have yet another system you need to learn with its own, consistency and availability and isolation and durability properties that you'll need to learn. So this looks pretty good. Now, I think for most folks, this probably you'd say that this is basically it, right? This is what a NoSQL database cluster looks like. Well, there's one final piece, and this is sort of getting a little bit down in the weeds, but you're going to also have to run something called a consensus protocol, right? If you're doing writes, where you're going to consider a write complete if 3 of the 4 nodes of the cluster have have said that they've received the write. You need to use a consensus protocol to make sure that those 3 or 4 nodes are actually coming to agreement on the fact that the write is complete, right? And there's a lot of different ways of doing this. There is a pattern called Paxos, which is pretty widely used, but these get very complicated, and you start to get into pretty deep sort of distributed computing concepts in order to make things work properly. And so you've got this other thing that you need to run here, and so you can see at this point now we're pretty much done. But that's quite a lot of infrastructure and sort of low-level protocol stuff that you need to both learn, run, and make work on an operational basis. And that's just a lot of stuff. And if you want to go one step further and maybe have disaster recovery or be able to go across regions, guess what? You got to do that again in another region. So you can see running a NoSQL database is not easy, right? Sure, possible to do it. EC2 makes it possible. We got a lot of customers who do it, but it is not something that I think anyone would legitimately describe as easy. So getting back to our question, why use a managed service? Well, DynamoDB is a managed service, and we run all of that infrastructure for you, right? So those architecture diagrams we just saw, I mean, that's not the architecture of DynamoDB necessarily, but DynamoDB architecture does have similar characteristics, and we're running all of that for you. You as the customer never see any of that. And when we do the demo, you'll see that you can be up and running with DynamoDB in just an amazingly short amount of time. So rather than spending the first 3 or 4 months of your project just getting the NoSQL system up and running and benchmarked and stable and scripted out and deployed, you can actually start writing your application and be up and running quickly. You get all the benefits and none of the operational overhead of running a distributed system. You get infinitely scalable read and write I/O. You get high availability within the region. Data is durably stored in 3 availability zones. You get cross-region replication. We'll talk a little bit about that. That's a relatively new feature to Dynamo, but really, really powerful. You can easily export data out of Dynamo into services like S3 that allow you to do all kinds of other stuff with the data. You can essentially define a trigger now using the Lambda service, which is a way of executing functions as a service. We have tight integration with other services that are part of the analytics and data ecosystem at AWS, like Kinesis and Lambda and EMR and Redshift. And then most importantly, you pay only for what you use when you use it, right? So if your system is not making a whole lot of reads and writes to the database at certain times a day, you can scale down your throughput and pay only for what you actually need at that point, which is something you absolutely cannot do if you're running all that infrastructure that I just showed you yourself. You're going to pay for every hour that all those EC2 instances are up and running, whether or not you're really hitting them with a fair amount of load or not. Okay, so now we know what DynamoDB is. It's a fully managed NoSQL database service that lives in the AWS cloud. Let's talk a little bit about the fundamentals of how you actually work with Dynamo. So the sort of root level entity in the DynamoDB service is something called a table. And a table is, more or less what you would think a table is. It's basically a collection of items. And items are analogous to relational database rows, but with one key difference, in that items can have an arbitrary number of attributes associated with them. So you can see from this diagram here, each essentially item in this table has a different set of attributes associated with it. And that's why Dynamo is called a key value store, because you can think of the attributes of an item as essentially key value pairs, and each item can have one or more key value pairs. So that's also why Dynamo is considered a schema-less database, because each item in the table does not need to share the same attributes as other items in the table. It's absolutely no problem if they all do, right? You can absolutely create a table that consists of items that look an awful lot like a relational database row. There's nothing wrong with that, but just know that there's no requirement that you do that. There is one specific type of attribute that every item in the table needs, and that's something called a hash key. The hash key is basically a way of uniquely identifying that item in the table. It also determines how the data is distributed, and we'll talk a little bit about how the partitioning that is driven by the hash key value is important for scaling DynamoDB in a couple of slides from now. Alternatively, in addition to the hash key, you can define something called a range key. So this is if you wanted to model a one-to-n relationship in the table. So you can think of that, say a hash key could be something like a device ID, maybe from a mobile device, and a range key could be a timestamp. Right, and in this mode, you're basically going to have multiple device IDs in the table, but no device ID will share the same timestamp. That's a classic sort of time series table. And you can create essentially a composite primary key, which will be the combination of the hash key and the range key. The range key also allows you to do very nice query capabilities. So you can do all the, equals, greater than, less than equals, greater than equals, things like begins with, between, sort, and counts. Just basically allows you to execute some very useful queries on the table. Data types, pretty simple. You have strings, numbers, and binary. You can also have string sets, number sets, and binary sets. Those are just basically sets of values that live as a single attribute in the table. And then for the document storage, and I will actually in the demo show you how to store JSON documents directly in DynamoDB. We have some additional data types: Boolean, null, list, and maps, and those are for storing the nested JSON. So let's talk a little bit about the hash table and why it's important. So the hash key uniquely identifies an item, and you can see here we have these 3 items. They look like they're employee records, let's say, where you have a name and a department. And you can see each item has a numeric ID, right? And this is not unlike what you would do in a relational database, where you would probably have some kind of identity column as your primary key, and every time you insert a new employee into the table, it would generate a new numeric ID. Well, the difference with Dynamo is that what we're going to do is we're going to actually take a hash of that numeric ID and place that hash into a hash key space. And you can see the hash of 1 ends up in hex space 7B, hash 2 ends up in 48, and hash 3 ends up in CD. And what this does is that you basically now end up storing this data in that key space on what we call separate partitions. And so essentially we now have an unordered hash index where the items are stored on actual physical separate partitions. And it's these partitions that allow us to scale. And we're going to walk through an example of how that works in a few slides from now. But basically the reason why we're going to split your items across separate physical partitions is because the partitions are what allow us to scale horizontally. We replicate the partitions across availability zones, right? So that's the 3-way replication, right? So you can see that partition 1, partition 2, partition n, we get 3 different replicas, and each replica is held in a different availability zone. So the availability zones, as you know, are physically distinct data centers essentially in a region, and by replicating your data across those availability zones, you can basically achieve a very high amount of durability, right? You now have data that's stored in 3 separate physical data centers, essentially. When you have a range key associated with your hash key, basically we're going to store the range key index alongside the items in the table, but we're going to create an ordered index. So essentially the hash index is unordered, but the range of values for those hash keys are ordered. And so you can see here, just looking at partition 1, we have customer number 2, which is in that particular key space of the hash table. But the orders for that customer, order 10 and order 11, are actually stored in order. So the range keys give you an ordering, and that's one of the reasons why you can do those like between and greater than or less than queries, is because we know based on the order of the index where those items are. You can also create something called a local secondary index. So a local secondary index is basically an additional range key, essentially. So if you have a hash key and a range key on your table, and that consists of your primary key, if you wanted to have that same hash key and a different attribute act as a range value, you could create what's called a local secondary index. And in this case, the LSI is going to be located, the index is going to be located on the same partition as the table itself. And so as a result of that, there are some limitations in terms of the size of that index. You can have a 10 gigabit max index per hash key on that table. A global secondary index is essentially another type of index that allows you to create an index on an arbitrary attribute in the table. So if you wanted to look up, do a query on items in the table on something other than the hash and or range key, you could create a global secondary index on any arbitrary attribute and basically be able to fetch only those items that match that attribute or the value of that attribute. Global secondary indexes are maintained separately from the tables themselves, and so as a result, the throughput, the read and write throughput of a global secondary index is managed separately from a table. The indexing is done automatically, right? So basically, as you update or insert items into the primary table, the DynamoDB service will actually update the GSI automatically. You don't have to take any action yourself to do that. So why use an LSI or a GSI? I mean, ultimately, an LSI can be modeled as a GSI. And so if your data size is going to be larger than 10 gigabytes, just go ahead and use a GSI. There is one limitation, you could call it, with a GSI, in that because it's a completely separate index on a separate partition, it is only going to be eventually consistent. Right, so you could read a value from the GSI that may differ from the value in the primary table if the indexing hasn't occurred when you do that read. So in that scenario, go ahead and use a GSI. Local secondary indexes can be either eventually consistent or strongly consistent. You actually have the choice when you go to read a data from the LSI, but a GSI is always eventually consistent. So that's a lot of stuff, right? You've got indexes, you've got keys, you've got tables and items. Pretty rich data model to work with here. You'd think the API would be complex, and actually it's not, right? This essentially is the API here. You can see we have a bunch of method calls for working with tables on the upper left there, and then a bunch of methods for working with items, and pretty self-explanatory, right? Get item obviously retrieves a single item. Put item writes a single item to the table. You can query, you can do table scans, and you can do some batch operations as well. So not a lot to learn, really. I mean, the API is simple. There are some things, some parameters that you can pass into these API method calls that you'll want to spend some time familiarizing yourself with. But at the end of the day, there's really not a ton of API methods that you need to learn. And then on the right-hand side, we have a very new and very exciting feature, the Stream API, which is basically a DynamoDB Stream is an ordered set of changes to items in your table. It's essentially like an audit log or a change capture data set for everything that's happening in your table. And you can do some very, very interesting things with streams. And there's a few additional methods that we've added for working with the Stream API. And we'll talk a little bit in a second about some of the emerging architectural patterns that we're seeing being enabled by DynamoDB Streams. And here's one of those right now. As a matter of fact, we have a service called AWS Lambda, which allows you to basically execute functions in response to certain events. And an event source for Lambda is DynamoDB Streams. So you can actually have function code execute to events that are occurring in your stream. That's basically a trigger, right? If a stream is tracking all the inserts, updates, and deletes to your items in a table, and you can write code that gets invoked when those operations occur, you can essentially now do triggers with Lambda and DynamoDB Streams. So that's a very, very powerful tool that you have at your disposal when you're working with Dynamo. This is another very interesting and powerful emerging architectural pattern that we're seeing being enabled by streams. The part of the diagram I want you to focus on here is that application NoSQL to Amazon DynamoDB in the middle there. You can see we have the DynamoDB stream coming off the back end of the DynamoDB table, and we can consume that stream with something like, say, Lambda, or we could write what's called a consumer application. And this DynamoDB Streams API lets you use the same Kinesis client libraries that you're already working with if you're using Kinesis to actually process data off the stream. And what you can do there is you can do some very interesting things where you could actually update documents and indexes in something, say, like Amazon Cloud Search or maybe even Elasticsearch cluster, and then also do cache updates to something like, say, an Elasticache. You're running Redis or Memcached. And that's really, really powerful because now you can basically take sort of real-time data that's being ingested into Dynamo and make it available in what I would describe as views of that data. So essentially you'll be able to create a real-time materialized view of that data in Cloud Search or in Elasticache. And then you can take advantage of, say, some of the full text indexing that you get with Elasticsearch or the geospatial indexing that you get with Cloud Search. You can take advantage of very low latency reads and more sort of object-oriented access to the data in, say, Redis or Memcached. So very, very powerful sort of architectural pattern that makes use of streams, and definitely something worth looking into. So let's talk about throughput. That's really a key concept with Dynamo, as well as understanding the hash key and range key concept. Throughput is probably the other sort of key concept that you need to understand. Throughput is provisioned at the table level, and you can provision throughput in terms of how many writes you need to do per second and how many reads you need to do per second. And so a write is essentially a unit of 1 KB per second, and a read is a unit of 4 KB per second. And so what you'll want to do when you're trying to figure out how much provisioning you need to do on your table, or capacity provisioning, what you need to do is just, given your approximate item size and the concurrency, the concurrent number of reads and writes that you need to do to the table, you'll come up with a number basically of read capacity and write capacity that you'll want to provision. The good news is that this is not fixed, right? You can always change it. So you can start with just some sensible sort of default values based on the understanding of your workload when you create the table. If you notice that over time, as your application gets more use, you need more capacity, you can go into the DynamoDB console and you can request more capacity. It's really, really simple. So you're not locked in at all with these capacity provisioning. So it's very, very nice. You can go up and down as you need to. Eventually consistent reads cost half as much as strongly consistent reads. So what that means is that if you're okay with getting eventually consistent data, and for certain things, like maybe you're building a blogging application, you don't necessarily need to have every client see all the comments in the comments thread all at once, right? It's probably okay if someone clicks refresh on their browser and then sees the latest, after somebody else may have seen it, right? That's a good example of an eventually consistent use case. If you do that, then basically you can read twice as many reads as you can with strongly consistent. Okay, so here's the example I alluded to earlier about why partitions matter in Dynamo, or one of the reasons partitions matter. So, if you can recall, when you create an item, you give it a hash key, and that hash key basically defines which key space the item's going to fall into, and the key space is linked to a physical partition. And so what this enables us to do with Dynamo, in addition to making the system distributed, is it allows us to scale. Right, and so in this example, let's say we have an 8 GB table size. So we have 8 gigs of data in the table. We need 5,000 reads per second, and we need 500 writes per second. So we want to look first at how many partitions we will need just to get the I/O throughput that we're requesting, and then how many partitions we'll need to get to store that 8 GB of data. So that first equation up there, you can see we have 5,000 reads that we're requesting. A single physical Dynamo partition can deliver 3,000 reads. So we're going to do 5,000 divided by 3,000, and then we're going to add in the write capacity that we need. So we need 500 writes per second, and a single partition can deliver 1,000 per second. So we end up with basically a 2.17. That's the number of partitions we need. Obviously, there's no such thing as a fractional partition, so we'll take the ceiling of that number. So that would be 3. And then for the storage, a DynamoDB partition can store 10 gigabytes of data. And so we have 8 gigs, so we need 0.8 of a partition just for storage there. And again, we're going to ceiling that to 1. And so to determine the number of partitions we need, now we need to just take the maximum of those 2, right? So we needed 3 essentially for the I/O throughput, and we needed 1 for the storage. So we're going to end up with 3 partitions. And that's how we scale with Dynamo, right? When you request more write capacity or read capacity, what we're going to do is we're actually going to move your data. We're going to copy your data across more partitions. And then if you want to scale back in and you no longer need as much capacity, we're going to basically copy your data to a fewer number of partitions. And that's why partitioning is so important with Dynamo. And this basically, just shows, given this scenario, we're basically going to get 1,600 and change reads per partition and 166 and change writes per partition. And each partition is going to have about 3.33 gigs of data on it. Okay, so let's talk quickly about some of the typical workloads and use cases, and that should leave enough time to go through a quick demo and then answer some questions at the end. So here's some examples of how you can model data in DynamoDB tables. We have a Woot online shopping site. It can use Dynamo to do a shopping cart, right? You can actually just have a table that stores all of the items in a user's shopping cart for that session, right? Pretty straightforward. And the nice thing is, because Dynamo is schemaless, each user can have an arbitrary number of items in their shopping cart, right? You can have 1, 2, 3, and you can have an arbitrary number of attributes per item, right? It's very, very flexible. You don't have to mold it all into a fixed set of columns and rows. AdRoll, big ad tech company that uses Dynamo extensively. They use Dynamo for some of the things that you typically find in ad tech, which are very, very low latency lookups, right? When you're serving up ads or deciding how much to bid on an ad, you generally want to be able to pull out some of that user profile information that you're pulling out of cookies and other session-based entities very, very quickly. And so AdRoll uses Dynamo extensively for that. And then finally, we have an example of a Wi-Fi enabled camera, right? And this is a great example of how you might do time series data in Dynamo, right? So we can define something called a queue point, which would have a camera ID as the hash key and a timestamp as the range key, right? And the queue point, essentially, that's the timestamp would describe sort of when in the video stream the interesting feature was detected. Maybe the camera is detecting motion, for example. So every time there's some motion, you're going to have a queue point for when that motion starts and when that motion stops. So that's a really good example of time series based data. You can basically, per camera, keep track of all of the interesting features in a video stream. And then you can create basically like a scrubber type UI where users can actually go backwards and forwards in the video stream and look for the what occurred during those queue points. Some of the other typical workloads we see, well, we just mentioned ad tech, really, really common, and Dynamo is very, very popular there. Internet of Things, we're seeing that increasingly more and more. Again, when you're reading data off devices, connected devices, you may have thousands, tens of thousands, perhaps even millions of devices. Dynamo gives you the scale to actually read or consume the data concurrently all across those devices. And it's also, very good for time series data, and that's oftentimes what IoT devices are sending. Gaming, another big one, right? Especially mobile gaming, saving game session state, game state. Dynamo worked great for that, especially, again, you can have 10 million people playing your game at the same time, and Dynamo can handle that. Web analytics, another classic sort of time series based analysis, clickstream data. Again, you're usually dealing with high velocity and high volume of data when you're building a web analytics framework, and Dynamo can handle both velocity and volume. Mobile applications of all types, right? You want to store user session data, application session data. Again, Dynamo works really, really well for that. And especially since you can actually make calls to DynamoDB through the mobile SDKs that we offer, Android and iOS, and you can do it in a secure way where you don't actually have to have credentials embedded in your application. So very, very nice and convenient way to store data from a mobile app. Large-scale websites, obviously, right? Like take the shopping cart example with Woot, right? Big e-commerce site, lots of concurrent users. Having the shopping cart not be available would be a really, really bad thing. Then people aren't actually buying things on your site. They're going to go someplace else. Dynamo gives you that availability and scale that you would need to make that work. And the important thing here at the sort of bottom line is, there are many, many more, right? This is just a very small subsection. It's a very, very versatile and useful database. There really are no right or wrong workloads for it. I suppose if you're doing things with heavy-duty entity relationships and very relational type data, that may be tricky to do in Dynamo, but you can oftentimes use it anyway if you choose to sort of denormalize some data and maybe model your data a little differently. So very versatile database that's good for a lot of different things. Okay, so with that, I am going to go into the demo here. Bear with me for 1 second as I break out of the slide deck and go and share my desktop. Okay, so what we have here, and hopefully everybody can see this, I have some very simple Node.js code that I've written here that is going to actually create a table in Dynamo. So you can see this is what, 28 lines of code here. This is all it takes to create a table in Dynamo with Node.js at least, but the other APIs or SDKs rather are pretty similar. And you can see some of the things of note here. The table name is going to be called shopping cart, so we're gonna model a shopping cart in DynamoDB. And I'm going to have a single attribute that I define called a customer ID, which is also my hash key of the table. So in this case, you can imagine if we're an e-commerce site, customer logs in, we know what their customer ID is, they can start adding items to the shopping cart. So let me go ahead and run this. Okay, so I went ahead and I ran that, and you can see I got a JSON response back. It tells me that the status of the table is creating. I can go ahead and, using the CLI, I can look to see if my table is created, and it looks like it has been. So you can see I can see this active down here. So that means my table is up and running, ready to go. Pretty easy, right? That took, what, a couple of seconds, 28 lines of code, and now I have a table and a fully distributed NoSQL key value and document data store. So very, very powerful. So now let's go ahead and let's put some items into the table. So in this case, I'm going to use the DynamoDB document API, which is an extension to the base DynamoDB SDK. You can download it directly from our GitHub repository. Basically, what it allows me to do is just insert JSON directly into Dynamo. And so you can see here I've got this shopping cart contents. You can see it's just a JSON object or document here. I have the customer ID, and then I have an array of items. Looks like here we're putting in some items for a new garage door. And you can see, one of the nice things is you can even use other services very easily, like S3, to store things like the images for those items. So you wouldn't want to put the images in Dynamo because Dynamo has some restrictions on item size, but you can easily have pointers to those larger objects into something like S3, which is much better suited for those. So I go ahead and basically I create this array of items, just a JSON object or document. And then essentially all I need to do is essentially just call this put item, where I pass in the name of the table and the array of JSON, or of items rather. That's it, right? That's all it takes to actually insert this into Dynamo. So I'm going to go ahead and run this now. And you can see in this case I got an empty response. The put item request doesn't give anything back. So now we want to verify, well, did we actually get something back? We'll go to do a get item. A get item is even easier, right? In this case, all I'm going to do is I'm basically going to say, here's my table, and here's the key of the item I want to fetch, right? So I'm fetching the item for customer number 1. That was the customer we used when we just inserted the items previously. If I go ahead and run that, you can see on the terminal window, it may be a little hard to see. I'll show you another version of this in a second. It basically returns the JSON document that we had inserted into the table. So very, very easy API, really powerful to put data in and out of Dynamo. There is one other thing I will show you very quickly here with just a little bit of extra work. I mean, when I say a little bit, I mean a very little bit. You can basically use Lambda and our newly announced API gateway to create a REST endpoint that will actually pull this data out of Dynamo. Let's see if this works here. And yep, I'll make it a little bigger. You can see I basically just created a REST. I had created a REST endpoint called a shopping cart. I pass in the customer ID, and you can see it pulls back my data. And just to show you that this is not canned, if I do customer 2, we haven't inserted any data for a customer 2, so I get an empty JSON. So essentially by taking the get item code that you see here and putting it into a Lambda function, which is really not much more code than you see here. It's almost exactly as is, and then linking that Lambda function to an API gateway endpoint, you can essentially have a full REST API up and running in a matter of minutes without running any compute or any databases directly on EC2. It's all done through managed services. So really, really powerful stuff, really good stuff there. So with that, I will stop sharing. That is the extent of my presentation today, and we will turn it over to our moderator for the last 10 minutes to answer any questions that have come up during the presentation. Let me go ahead. I think I can find the questions that are mine. I can go ahead and start answering these here. Let's see. Okay, let's start with the question here. Is the composite key implicit or logical, or does it have to be created? So if you are using a composite hash and range key, you would need to, it has to be explicit. So when you go to create the table, what you would do is you would basically list both the attribute that represents the hash key and the attribute that represents the range key in the key schema part of the response, or the request rather, to the table. So you do have to create it, and it is something that needs to be defined at table creation time, but it's relatively straightforward to do it. Okay, let's see. Let me pull up this question here. If I make a query on a table using the hash key and a range key, and there are items that do not have the range key, are they excluded from the result set automatically? They would be excluded, right? So when you're querying by the primary key of the table, whether it's the hash key or the hash key and the range key, they would be excluded. But you need to be a little careful here, because remember, the key schema for the table is something that's going to be shared by all items. So whatever attribute you define for the range key, by default, all items, when you go to insert that item in the table, will need to have a value for that range key. But certainly if you do a query and you're querying on the set of values for a given range, any item that doesn't have that value will be excluded from the query. Let's see here. Is it possible to do wildcard queries, like say, give me all items regardless of hash key, where the range key is between X and Y? The answer is yes, but you would typically have to use either local secondary indexes or global secondary indexes to do this. And this particular example, what I might consider doing in this case would be to model the range key also as a global secondary index. And that way then you can say, give me all the items that match this criteria for the values of the items in the index. So there's lots of different ways you could model it, but that would just be one that you could use. And let's see. I think we have a few minutes here. It looked like there was one question up here that was already answered. The difference between Dynamo and Mongo. Another question about Dynamo and Mongo. Well, so there are some differences, and the differences are pretty extensive when you get to the architecture. Mongo is set up fundamentally very different than Dynamo in the way that it uses replica sets and master nodes, and the way that it deals with consistency and resolving conflicts when network partitions occur. So I think those are sort of kind of more advanced than what we can talk about here, but that is something that you would want to consider when you're choosing between the two. In terms of the access of data, Dynamo is going to generally have smaller items. MongoDB can handle larger documents than Dynamo can. Dynamo is generally going to be more optimized for scale. So again, you'll be able to independently tune read and write throughput with Dynamo, which is not something you can as easily do with Mongo. But there are similarities too, right? Dynamo can store JSON directly in the items, and just as Mongo can store JSON documents. I would say the biggest difference is that Dynamo is really more of a transactional system. It's great for smaller items that are being written and read in a high concurrency environment. Let's see, is indexing done as soon as return of the success signal? So for the local secondary index, yes. When you get the 200, HTTP 200 back, that would mean that the LSI has been indexed. I would actually, I should take that back. I will need to double check that, because you can actually specify a eventually consistent or a strongly consistent read off a value in a local secondary index. But because you can get a strongly consistent read, I think that may mean that it actually does the operation when you do the write. Now, for a global secondary index, we will update the index on write, but it's going to happen asynchronously, right? So when you get the result back that the write has succeeded, it is possible that a client reading that same item out of the global secondary index would get a stale read on that, or an eventually consistent read. So for LSIs, because you can specify strong consistency when you read off the LSI, you can guarantee that essentially after a write has occurred that all clients will see that write, but for global secondary index, you won't. Let's see, can we programmatically alter read and write throughput for a Dynamo table via a Lambda function event handler? Yes, you can. Through the update table API call, you could basically increase or decrease the capacity. So if you have a Lambda function that's doing something and you wanted to scale out your DynamoDB table in the body of the Lambda function, you could. It does take a little bit of time to copy data to the new partitions if you're scaling out, though. So just keep in mind that when you update a table to increase your throughput, it's not instantaneous. So I think you'd want to be a little careful in trying to do this in a way that's sort of expecting kind of real-time behavior. Again, you can do it with a Lambda function simply because Lambda allows you to make API calls to Dynamo, but I'm not sure that's necessarily something you'd want to do. You'd want to be a little careful with that. Can DynamoDB validate data JSON against a JSON schema? To my knowledge, no, that is not supported today. Basically, the JSON document just gets converted to those set and map and list data types that I showed in the presentation, but there's no validation against a schema. Okay. Let's see. I think there's one more question just came in here, and we got just a few minutes left. Is there an effective way to manage a one-to-many relationship in Dynamo? Well, probably the easiest way would be the hash key plus range key, right? That's you can do it all in a single table, and that works very well. You would not necessarily want to do it in the way that you would with a relational database, where you would have a primary key in one table and then carry that primary key over as a foreign key into a second table. The reason is that there's no way to do joins on those tables in Dynamo. You could join in your application code, but that gets a little ugly. So some of the other techniques that I've seen, if you did have to manage a one-to-many relationship that spanned tables, would be to make like a denormalized composite key in the child table, where it might be something like the hash key of the parent table and then a delimiter like a colon or a comma or something, and then the child key of the item in that table. And then that way, at least your application could construct a hash key value to fetch those individual items from the child table. But it would have to basically do a batch fetch. It would have to create all the hash keys for all the items it wants to fetch, and then essentially do a batch item fetch, which would fetch them en masse. But it's essentially doing one by one. You send it a whole bunch of hash keys, but you're essentially doing single fetches on items in the child table. Can the query use regex to match items? I don't think so, but I would encourage you to read the query docs. It's been a while since I have looked at them in detail. There may be some wildcard type matching you can do. I don't think full regex support is there. But again, take a look at the query documentation, because it will show you specifically all of the types of query operations that you can do in Dynamo. Can you use location data for secondary index? Yes, absolutely. You could do geo coordinates for the secondary index. We don't today have the ability to do a geospatial query against that data, so that would be an excellent example of where you might want to use DynamoDB Streams to basically take those geolocation coordinates and then say update an an Elasticsearch cluster or index, so that then you could do the geospatial query via Elasticsearch. But absolutely, you could store maybe a number set where an XY coordinate or something are the two values of the set. Okay, we're at the top of the hour here. So again, I thank you all for taking the time. I encourage you to play around with DynamoDB. There is a free tier that you can use, so you can get started without actually having to pay anything. Definitely encourage you to look at it, and hope that you will join us again for future webinars.